Hi everyone. Thanks for coming to the PhD student colloquium. Today's speaker is Yuan Li, who did his undergraduate degree in Beijing, and then did his master's degree in Georgia Tech, both in mechanical engineering before coming to Penn. So today he's going to talk to us about his recent work in magnetic energy density. So without further ado, Yuan, you have the floor.
Thanks for the introduction. As you know, I'm a mechanical engineer, right? So it's a little bit not appropriate to talk about my thing in the ESC, but I will try to talk to you a little bit about my research, the permanent magnet that's micromachined, and their application in the magnetic MEMS devices. So the past few years, right, people jokes about that they are the years of the things. So you hear the commercials about boasting that their product is the next big thing. So I'm a MEMS guy, so what I really care about is what's the next big thing for MEMS, right? So what are the most driving, what will be the driving force for MEMS in the future? But I guess before that, I have to talk about what's MEMS, right? Some of you probably are not familiar with it. MEMS stands for micro-electromechanical systems. So in my implemented definition, they are small-sized gadgets or small machines that can be used as sensors or actuators. So by small, I mean normally it's in nano to micron size, the characteristic size. The whole package might be in a bigger size. So one of the common notion is that the Internet of Things, right, will be the next driving force for MEMS. Why is that? So the MEMS sensors are eyes, ears, and noses for IoT. I will give you a few examples over here. There are three big categories, right? Your body, your home, and your city. So for your body, and when you do sports, right, the wristbands and wearable devices, some of those have some inertial measurement unit, accelerometers and gyros. And for medical devices, it's also a popular notion, right? You have this blood pressure sensor or glucose sensor that tests your body condition and wirelessly sends the data to your doctor. And then they do the diagnosis and give you the feedbacks. Right, that's for the body. And for your home, that I think we all survive the Philadelphia cold weather here, right? So I guess what I want is before I go back to home, right? I want my home to be warm and cozy. So one of the things that we can do is the humidity and temperature sensor that will check your room temperature, and you might be able to control through your apps, through the phone. So for a city, the pollution is a big issue, especially in developing countries. And I'm from China, so I know how important it is. This environmental detection sensor can also play a big role, right? So my research is a subset of MEMS devices. It's magnetic MEMS. So magnetic MEMS is based on the electromagnetic interactions between the magnetic material, the component of one of the MEMS devices, with the active or passive magnetic field sources. So active is normally a current carrying coil, and a passive source is normally a permanent magnet, which will be my topic. So I'll give you a few examples of the MEMS devices. So on the top, this one is actually a MEMS switch. So in some of the applications where you require high off-state isolation, MEMS switch is actually better than the solid-state devices like transistors because of leakage. So here's one example that they have this solenoidal windings over a permanent alloy stator. And there's an air gap over here that once activated, this moving part is sucked into here and drag this gold contact to get rid of the resistance. They will attach this stationary gold contact. And of course, there are springs that are designed to push it back once it's deactivated. So another example is a micrometer. This is very similar to the traditional, not traditional, but the TI branded DMD devices. But other than this, using the capacitive, they use the electromagnetic interaction over here. And of course, one of the very classical magnetic MEMS devices is a micromotor. And this is one of the devices that we used to have in our group. So we mentioned that the permanent micromagnet is the passive magnetic source. So it's actually in some perspective it's actually better than the current carrying coils, both as you can see that in the energy efficiency as well as in terms of scaling. So I want to give you a few examples on what are the existing approaches to fabricate this permanent magnet. Let's go from the bigger scale to the smaller scale. So in the bigger scale, in the bulk scale, right, sintering by powder metallurgy is definitely one of the dominant techniques. That you have this molten alloys in basically a protected environment in an inductive furnace, and you melt it up, and then you pour it into a mold. So once it's solidified, we have this kind of bigger shaped magnet. And apparently this high temperature is normally 1,000 degrees C, is incompatible with the CMOS process, right? But more importantly, I think it's the scale that is too big for MEMS devices. So one way you can still utilize the sintered magnet is you further processing it. So for example, you can do the laser micromachining that we have an expert in our group to do this. In a similar length scale, that you can use the bonded magnet. So it's called a bonded magnet because it uses magnetic powders. They load the powders into certain polymer, and then you can use different techniques. Either you do a screen printing-like technique, you lap the thing into a prefabricated trenches, or you blend this polymer with some photosensitive, blend this powder with the photosensitive polymers, and then you can use traditional lithography to define it. The powder is normally in micron size, tens of micron size. So if you want to fabricate a thinner magnet, apparently the length scale is much thinner than over here. You can use electroplating is one of the methods. So here you can see that it's a cobalt nickel manganese phosphorus alloy plated through mold, the traditional UV-defined photoresist mold. And if you want to actually plate it thicker, there are some constraints, which I will talk about later. So a sputter magnet normally is even thinner, and the speed is slower. Right, so as we mentioned that, there are some length scale that is specifically important to MEMS. It's normally 1 micron to hundreds of microns is the perfect permanent magnet length scale for MEMS. Yeah, so I will talk about, before I go to the main part, I will give you a quick refresher on a few magnetic properties that's important, especially for permanent magnet or hard magnet. Right? The remanence and coercivity is defined by the hysteresis loop, the intersect of the hysteresis loop to the BM axis and HC axis. And both of these two parameters can be captured in one single parameter, the BH max. It's defined as the maximum rectangular area underneath the BH loop in the second quad. And this is one of the primary parameters for characterizing hard magnetic materials. So in the previous slides, all the properties are volume-independent property. And in terms of on a device level, right, what we're really interested about is you apply this certain magnetic material, and you hope that the performance of your device is improved. So it's important to understand whether on the device level, whether it's the volume-dependent property or independent property is of matter. So in order to understand that, let's see a few examples. The first one is a magnetic compass. This is one of the possible designs utilizing the permanent magnet. So interaction between the earth field and this permanent magnet will create a torque. And the torque will be further sensed by the piezoresistive strain gauges and to determine the direction of the field. So the governing equation shown over here, the torque both the torque and the sensitivity, is proportional to the volumetric magnetization, V times M. So this is a volume-dependent property. Right? Another example is a vibration-based energy harvester. So the governing equation is well known, the Faraday's law. The induced voltage depends on the rate of change of flux rather than the flux density. Right? So the B times S is similar to a V times M, is a volume-dependent property. So it's clear that on the device level, we really want a volume-dependent property. Right? So given a constrained MEMS footprint, what we really want is large thickness and high energy density at the same time for a permanent magnet film. So then you say, you just deposit thicker films. What's the problem? It wasn't that easy to scale up. So one of the problems you have is this property deterioration. As one of the examples shown over here, as you see that the magnetization and the BH max both decreases when the thickness goes thicker. And note that tens to hundreds of microns actually will be really interested in the MEMS devices. And one possible explanation for this is people found out that the grain size of the film increases as the film thickness increases, and it's directly related to the hysteresis loop shape. And so for the BH max, you can see that as the thickness increases, the BH max decreases in this case. So that's not the only problem. The other problem is the mechanical stability. So in general, these hard magnetic films possess very high residual stress. And as you know that when the film thickness increases, the stored strain energy inside the film also increases. And according to the Griffith's criteria in the fraction mechanics, right, when you have the stored energy, the energy release rate when it's higher than the fracture toughness, the film will have a spontaneous cracking or delamination. So what that really means is there is a critical film thickness of a film have certain residual stress that beyond which the cracking will happen. And this critical thickness is proportional to 1 over the stress square. So given all this constraint, right, is there a way to have both large thickness and high energy density at the same time? And we see that, as thickness grows, the property decreases. And one thought is that since, you suffer from this property degradation, when you get a thick film, why don't you have the thin films and stack them all together? Right? So you can get both good property from the thin film, but also have a very large thickness. So there are several ways to technically realize this. One of the way is you do a self-assembly sort of thing, that you are able to bring the films together with some favorable forces, let's say capillary forces. But one problem with that is the alignment between the layers is hard. And sometimes in applications that you want a precise location of your magnet, and then that would be a problem. So the way that we utilize over here is sequential multilayer electroplating. So it's sort of a self-register process that is plated through the mold, that you have the thin film A, which is the magnetic material, and some kind of a non-magnetic material, and you plate it in a lamination structure to have this AB microlaminated structure. So first, let's talk about the material selection part. Right? This what we call a unit cell of this laminated structure has two parts. So first, talk about this magnetic layer part. So as we see that, if you want to go have a very thick film, the deposition speed definitely matters. And for the vacuum-based process like sputtering, it's relatively low speed, and also it's less economic comparing to the electroplating. So what we use here is electroplating so that this magnetic film should be compatible with electrodeposition. And also, very importantly, that we would like to tune the direction of this anisotropy in the same direction. right? So for a thin film structure, the in-plane dimension is much larger than the outer plane. So the shape anisotropy lies in the in-plane structure. It will be beneficial if we can tune the magnetic anisotropy also in the in-plane structure, in the in-plane direction, so that the overall property is boosted. So there are lots of existing magnetic alloys. I won't go into the details of it. But if you want a CMOS-compatible and integrated fabrication approach, cobalt nickel phosphorus is one of good choice. And this is the magnetic system that we used in this study. So for the non-magnetic material, we call it interlamination layer. So other than good electrical conductivity, we needed to have a very low residual stress, so that the average stress is reduced. We'll talk about this later. So it is hypothesized that this non-magnetic layer should have an excellent planarization properties in order to fully reset the surface of the underlying magnetic material, so that the subsequent layers is well plated. And this is very important because we know that the interface and substrate have a very important physics implication on the material properties of the multi-layer structure. So it's one of the biggest concern over here. So what we chose is a very shiny, smooth surface copper. It's a commercial bath, and it contains levelers and brighteners for this interlamination layer. So the next thing to do is to optimize the plating conditions and bath conditions in order to achieve what we proposed in the material selection guideline. Right? We want a large in-plane energy density as well as a in-plane anisotropy. So based on the existing literature, there are several important parameters we choose to fulfill this goal. So the fabrication part, this is a very traditional through mode electroplating. You have an insulating layer deposited onto a silicon substrate, after which you deposit a seed layer for electroplating. And of course, you have to have a very thick mold in order to plate thick layers. And basically, after that, you remove the tie seed layer, and then you have a traditional electroplating. But we utilize a robotic controlled system to do the multi-layer electroplating. So we use the cobalt nickel phosphor bath, which we customized to optimize the property, and the mirror copper bath, as we talk about. So I'll show you a video about this process. And so first of all, you have one layer of cobalt nickel phosphorus plated, and in a void of contamination, you have this rinse bath over here. And then you grow another layer of copper. Right? It's simple, A, B, A, B, A, B. All right, so after electroplating, you remove the mold, and you basically inspect your cross-sectional image in SEM. And here we show a 10 pair laminated magnet, and this is a enlarged view. So we do a selectively copper etch, wet etch, so that to give you the contrast. This white protruding layer is cobalt nickel phosphor, and the receding layer, because of its etched, is copper. So after the optimization, right, what do we get? So here is the 1 micron thick single layer cobalt nickel phosphor films measured by VSM to check the magnetic properties. So as you can see, that as desired, we have a relatively large in-plane BH max compared to the outer plane, and also the magnetic anisotropy lies in the in-plane direction. So as we mentioned in the introduction, right, if you have a very thick film for a lot of permanent macromagnetic systems, that the energy density drops as the thickness increases. And it's the same in our system, the cobalt nickel phosphorus. As you can see, that there's a sharp drop between 1 to 10 micron. So one other thing you can do is from this plot, you can find out in this plot is that you can determine the magnetic layer thickness in this laminated structure, right? Certainly, given the assumption that you can retain or preserve the thin film properties, the thinner of a magnetic material choose, the better property it is. But there is a trade-off, right? If you have to choose a very thin layer, that the process complexity will be increasing. But definitely you won't want to choose something that already sharply decreased. Right? So 1 micron, that's what we choose over here, to be the magnetic layer thickness. So we also want to check using XRD whether we have the well-defined in-plane anisotropy, I mean the in-plane texture. So as we see that a relatively large HCP 100 peak comparing to the 002. I didn't show the powder the data from the powder form, but as you will see that this in-plane peak is much higher than the outer plane, indicating the c-axis of this HCP structure is aligned in the in-plane direction. So before we go to the laminated films, I want to mention a few things. So we introduced this notation to represent the laminated magnet. The T cobalt nickel phosphorus is the cobalt nickel phosphorus thickness, so as the copper. And N is the number of pairs. So one pair is composed of one layer of cobalt nickel phosphorus and one layer of copper. And the total magnetic thickness is the sum of the cobalt nickel phosphorus, so is the copper. The total thickness is the sum of these two. And one important thing is the field factor. It's defined as the total magnetic thickness over the total thickness. So as you see that, other than the first layer of cobalt nickel phosphorus, all other magnetic layers is built on the underlying copper layer, right? We know that the interface has an important role in the material properties. So we want to do a controlled experiment to understand the underlying role of this copper interlayer. So here we do is we have a 5-pair cobalt nickel phosphorus, 1 micron, and various copper thickness. And we measure the top copper layer roughness using AFM. And this is the some representative scan shown over here with the increasing of a copper interlayer thickness. And for your reference, the seed layer copper is shown over here, and the single layer 1 micron cobalt nickel phosphorus is shown over here. As you can see that when you increase the interlayer thickness, intuitively it smooths out the surface. The detailed roughness data is shown over here. So RA is the arithmetic mean, and RQ is the root mean square. As you can see that when the interlayer thickness increases, the roughness decreases and plateaus. And it's bound by two limiting scenarios, the 5 micron single layer cobalt nickel phosphorus and the seed layer. So there are two things that you can draw a conclusion from this plot, is that the 5 micron single layer has the highest roughness, as expected. There is no planarization effect. And the increasing of the copper layer have an increasing planarization effect to smooth out the surface towards the roughness of the seed layer. And we also do XRD on these laminated structures to compare with the single layered counterparts. And by comparison, we found out there's no additional or missing peaks for the cobalt nickel phosphorus. But there's one thing that changed. By analyzing the peak 100, we found out that using Schrödinger equation, the green size decreases as the interlayer thickness increases. And this is very similar to the trend of the roughness, and it's bound also by two extreme cases, the 5 micron and 1 micron single layer case. Of course, we'll also do the magnetic measurement by VSM in this 5-pair lamination. And interestingly, you can see that both the energy density and the coercivity increases as the thickness increases, but the remnants keeps relatively constant. This is within 7%. So I want to draw your attention to this specific point. So there's a very important implication over here, that this is the copper thickness equals to 0. So what this means is actually the robot pulls up the thin film every 1 micron for 5 times because it's a 5-pair lamination. So this, you see that this means by purely interrupting the electroplating periodically doesn't help to increase the magnetic property. What really important is the planarization effect from the interlayer. So now you know the chain reaction, right? So the increase of the copper layer will reduce the interface roughness and further reduce the cobalt nickel phosphorus grain size, and finally influence the property, especially the coercivity and BH max. So the interplay between the grain size and the coercivity specifically can be understood by a theoretical model proposed by Herzer. So basically it says that for a assembly of small grains, the computation between the anisotropic energy and the exchange magnetic energy determines whether the coercivity is proportional to d to the 6th power or 1 over d. So the dividing point is when the grain size equals to the exchange length. So for our system, cobalt nickel phosphorus, the calculated critical grain size is 5 nanometer. As you recall, the grain size lies between 16 to 24 nanometer, which is on the right side of this 5 micron. So this explains this inverse relationship between the grain size and coercivity. So we mentioned at the very beginning, right, the mechanical stability also is one of the important factors to limit the overall thickness. So we want to talk a little bit of that. So there are several ways you can reduce the stress so that you can increase the thickness. This includes, but not limited to, these few things. Let's say, for example, you change the current density, or you change the additives, or use some other techniques. But as we know that the magnetic properties are very sensitive to the plating conditions. And for some of the cases where the magnetic property is predetermined, let's say you want a specific coercivity, or let's say you want an in-plane anisotropy bigger than the out-plane, then this techniques might fail short. One alternative way is to stack your targeted film with some auxiliary films that has a compensating stress conditions. For example, a low stress or a negative stressed condition. And the studies show that for multilayer structure, the average stress can be presented in a individual layer weighted stress. Under the assumption that the thickness of your multilayer is thin, and also everything runs in the linear elastic regime. So we want to actually understand whether this formula applies to our system. So we measure the residual stress of a single layer and multilayer structure by a profiler based on the Stoney equation utilizing the film curvature. As you can see that the relatively low stressed copper single layer reduces the average stress of the cobalt nickel phosphorus to almost half of 1 micron, single layer, and 5 micron, single layer. And note that this measured stress has very close, the error is less than 2.5%. So after all this analysis, right, what a device guy really cares about is you use this, no matter whether it's a single layer or it's a laminated magnet, as a black box. Right? So you plug and play into the device, and hopefully the one that you propose have a better property. So the advantages of this laminated structure can be demonstrated utilizing 2 cases. The first one is when the magnetic thickness is of concern, and the second one is if the total thickness is of concern. So let's talk about this case first. So as we know that there exists very high residual stress in the magnetic layer. And along with the fact that when you increase the magnetic thickness, the total strain energy also increases. So in this sense, the delamination would be the factor that prevents you to get an even thicker film. So in this case, the total energy is related to the magnetic thickness rather than the total thickness. And here we show you a plot of a BH max versus the magnetic thickness. So the strategy of this case is actually you want to pad the individual layer thicker, right? So you can both retain the good property of the thin film, but also reduce the average stress to improve the mechanical stability. So here we chose a relatively thicker copper film. And as you can see that the energy density was relatively well kept in the multi-layer structure as comparing to the single layer, which is plummet in this 1 to 5 micron region. And because of this, we were able to have a relatively larger total magnetic energy in the microlaminate case comparing to the single layer. So another case is when the total thickness is of concern. Now, for example, let's say the MEMS devices, the MEMS module resides in a prefabricated silicon trench, right? So the total thickness is constrained. And then we have to think about the strategy here, that even though, let's say, you decrease the copper interlayer thickness, you have a worse, you less preserve your magnetic properties, but this will be compensated by the fact that you actually now have a larger magnetic thickness because the overall T is constrained. So in this case, it's the total thickness that matters. And here we show you a plot comparing the fill factor modified BH max versus the total thickness. And here are some possible designs where you can utilize the fill factor, the opposing effect of the fill factor, to achieve that with the same total thickness, your laminated structure can still have a larger total magnetic energy comparing to the single layer. So to summarize, we propose a laminated permanent micromagnet that enabled by an integrated and CMOS-compatible fabrication approach. We demonstrated that the overall total magnetic energy can be improved using this laminated structure in different scenarios. And we also understand the underlying mechanism, emphasizing in the interplay between magnetic properties, the interface conditions, and the crystal green size of the laminated structures. That will be my talk. Thanks. Welcome any questions.
Have you looked at the magnetic field for in-plane multilayer structures? Close to the surface, the edge?
So we haven't yet. And I guess the next step probably is use the console to simulate that first, because that's also related to the next step, to the device level. But I understand why you asked that. You want to ask whether there's a closed loop of the flux or not.
Or an oscillating field pattern.
Right. Yeah. Right. Yeah, we haven't done that yet.
Are there any more questions?
So MEMS is very, very practical and kind of aggressive.
Mm-hmm.
So in terms of the mass production, what would be optimize the process time? For example, stacking up to 500 layer or 100 layer. What will be your targeting process time?
So I think that's a very good question, and as you know that this also relates to the precision of the process, right? So for example, for the self-assembly case, right, you can basically utilize the spatial you use the space in terms of to change for the time, right? If you can self-assemble it in some way that you can have the very small amount of lamination but a very large area, and then you bring it together, right? That's all depends, I think, on the device itself. But I think for this specific process, that you have very knobs to control about your total time. It's always depends on the current density that you choose, right? That's also related to the magnetic property. So I think it's fairly constrained if certain amount of certain magnetic property is targeted. Of course, if you are pretty flexible with that, you can change the current density and such.
I think let's thank the speaker one more time.